Hello, I'm Dr. Ian McCullough of Johns Hopkins University. This is a short lecture on social network analysis, closeness centrality. There are two learning objectives. The first is to differentiate between the four basic centrality measures as the two previous lectures in this series. In this particular lecture, we are going to focus on closeness centrality and calculating that by hand. Again, students that calculate these measures by hand are 11 times more likely to understand the difference between the four of them up to 3 months after the course. This is Dave Krackhart's data set to illustrate the differences between the four centrality measures. You'll notice that Linda has more connections than any of the other nodes in the network. That is degree, the most connections. You'll see that Conrad has high betweenness centrality because he's on the shortest path between pairs of nodes in the network. He really spans this cluster to this cluster over here, and that is what gives him his high betweenness centrality. He is in the middle of these paths. Linda is also high in eigenvector centrality. Eigenvector centrality usually indicates somebody that's connected to highly connected others. Closeness centrality today is what we will focus on, and that is Roger. Roger, although he has less connections than Linda, is one step closer to all the people on this side of the network. Therefore, his average distance to everybody else in the network is smaller than Linda's, and thus he has better closeness centrality. Again, degree is the number of connections. Betweenness is the extent to which it lies on the shortest path between others. Closeness, our focus today, is the average of the shortest distances to all other nodes in the network. Eigenvector is a measure of the extent which a node is connected to influential others. We use degree to explain the overall exposure to the network. Who would we think intuitively would be important? Betweenness is a measure for informal power. That is the brokers of knowledge resources and other things throughout the network. Closeness is used to estimate the time to hear information, indirect influence, diffusion processes. How do you get knowledge and resources from one node to everybody as quickly as possible? That would be closeness centrality. Eigenvector centrality is connected to influential others. We are focused again on closeness centrality. That's the average of the shortest distance to all other nodes in the graph. It is a measure that estimates the time for diffusion processes. So a high central node, a high closeness centrality node gets a disease. That disease is more likely to spread to others. Rumors are more likely to diffuse to others if it hits the high centrality closeness node. Here's our network. We are going to begin with something that looks like an adjacency matrix, but is a little bit different. The distance between node 1 and node 2 is 1 step. Same with agent 1 to agent 3 and agent 1 to agent 4. Notice what happens when we go from agent 1 to agent 5. We indicate a 2. This is not an adjacency matrix. It is a distance matrix. It is saying how many steps does it take to go from one agent to another agent in the network. When we look at agent 2, again, 1 step to agent 1, but there is now 2 steps to agent 3, 2 steps to agent 4. Granted, you can go agent 2 to 1 to 4, or 2 to 5 to 4. There is still 2 steps in the shortest path. We're not interested in which path it is. We are just interested in the length of the shortest path. So for agent 3, that will be even higher, right? 2 to 2, 2 to 4, and 3 to 5. We can complete this for the other nodes in the network. So we now know what the distance is. So, like collecting any average, we are going to sum across the row to identify enumerate the size of the paths, and we are going to divide by how many paths exist, which is n minus 1, in this case 4. That tells us that the average path length would then be 5/4, 6/4, 8/4, 6/4, 7/4. However, because if we did that, we would then have the most central node having the smallest value and the most distant node having the largest value, because we're talking about a distance measure. So the way we scale this so that it is comparable with the other centralities we are familiar with is we take the reciprocal of that. So our closeness value ends up being, instead of 5/4, 4/5, 4/6, 4/8, 4/6, 4/7. By inverting that, we are then able to have a scaled centrality value that scales between 0 and 1 and is more easily compared to other centrality measures. So in review, we are taking a distance matrix, not an adjacency matrix. We are taking the average distance, and then we are inverting the average distance to get the closeness centrality value. Here is the network where the nodes are sized based on closeness centrality. I will ask you to pause the video, take the network that you see here, and calculate closeness centrality for all 6 nodes in the network. Now that you have paused the video and calculated the closeness centrality of each of these nodes, we will go through the solution. You see the network still. Here is the distance matrix for the video, or for the network that you see above. Take a moment to make sure that it is the same as the solution you came up with. Summing across each of the rows, we have the following. There are n-1 possible paths, so 6 minus 1 is 5. And then we must invert that to get a closeness centrality values that you see here. And the network above is the same network where the nodes are sized by their closeness centrality. Please pause the video again and make sure that you have the same solution as the one that was calculated here. Again, closeness centrality often throws a loop in your ability to calculate the other centrality measures. Some of the differences are the fact that it uses a distance matrix instead of the adjacency matrix like the other calculations do. The inversion of the average is another problem that people often have. It's common when people learn how to calculate closeness centrality by hand, it affects their ability to calculate the other centrality measures by hand. So in the next lesson, we will give you an opportunity to calculate all centrality measures for a small network. But it is important that you do some practice on not just closeness centrality, but the other centrality measures as well. Thank you for taking the time to listen to this short lecture on closeness centrality. This is Dr. Ian McCullough of Johns Hopkins University.